A loop of wire in the shape of rectangle width W, length L, and a long straight wire, long meaning infinite, carrying a current I, lies on a tabletop as shown in the figure below. Determine the magnetic flux through the loop. Due to current I, use any variables stated above. And necessary. Okay. A loop of wire is that. Okay. So the idea here, the concept is, let's see, start with writing what flux is. Flux is B dot A. It's a dot product between the magnetic field and the area vector. The area vector is the normal vector with a magnitude that relates to the size of the area. And the direction is going to be normal to the surface, normal to the plane. And the direction of the magnetic field is going to be the right-hand rule. It'll probably look backwards because of the camera. That's okay, you'll get over it. Place your thumb in the direction of the current, wrap your fingers, and we see that the magnetic field goes this way around the loop. That means that right here, the magnetic field is going into the board. And so, yes. Now the issue here is the magnetic field for an infinite line due to wire is going to be mu naught I over 2 pi r. And this is just something that is often memorized. So you don't have to derive this every time. I think it comes from Ampere's law. Probably. You're allowed to memorize it for these classes normally, almost always. And so the idea here is that the magnetic field is going to be strong close to the wire, weak far from the wire, weaker, and so it's not going to be consistent. And so where your thought process there is integral. So we're going to start with our formula for flux. So I'm going to say a small bit of flux. You see, a small bit of flux is going to be magnetic field times a small bit of area. So the way I'm going to set this up is, this is all true, this all, oh, get rid of that, though true, not pertinent to my current discussion. So I'm going to say that we're going to do little delta r here. So this little distance, I'll call that delta, yeah, I'll call it delta r. So it's a small bit of radius from there. And this is going to be a length L. And we're going to look at these areas going down. And since this area here is at a constant radius, we can then basically just do the integral for the beginning to the end. And this area, this section right here, I'm going to call this delta A for a delta area. It's just going to be L times delta R. So I'll try and set this up, you'll see. So, yes, so B is mu naught I over 2 pi r. Delta area, as we said, was the length, L. I know they use capital L, I use lowercase l, same L, not important. Delta R, and that's going to be a little bit of flux. Rewriting this, so to solve this, we have a delta over here, delta over here. We're going to integrate both sides. So the integral of delta flux is going to be flux. And that's going to give us integral mu naught I 2 pi r times L dr. Now all of this is constant with the exception of r, the radius, which is getting bigger. And this is going to be mu naught I over 2 pi times L integral 1 over r dr. And specifically, we're going to integrate this from r initial to r final. R initial is going to be h. R final is going to be w plus h. So we're going to have something like h w plus h. All right. So now, harking back to calculus, the integral of 1 over r is natural log of r. So we have mu naught I L 2 pi natural log of r evaluated from h to h plus w. I get to w plus h, same thing. Plugging that in, we get mu naught I L 2 pi. I'm going to write this as natural log of h plus w minus natural log of h. And we could combine these. I'm not going to. Is there a good reason to combine them? Maybe. I'm not sure. Basically, we could do natural log of h plus w over h. Log rule. Not important. Might be important. We'll keep that as a possibility for later. All right. So, actually, I can just copy and paste this right now. Huzzah. Making life simpler and easier for everyone. Except it's too big, but virtual whiteboard. So there. Huzzah. And I'll just do a little arrow. Arrow. Suppose the current is changing with time according to current equals A plus BT, where A and B are constants from the magnitude of the EMF, electromotive force, voltage, that is induced in the loop if B is this, H is that, W is this, and L is that. All right, one thing we have to be careful with is this is in centimeters, and that's in meters, that's in centimeters. Okay, so we're going to use, I don't know if this is Lenz's law, Faraday's law, it's a law. So EMF equals negative d flux dt. One of them gives you direction, the other one gives you magnitude. When you put the negative in there, it basically combines both direction and magnitude, so that's fine. We already just found flux above, so this is going to be, I'm going to write this as mu naught L over 2 pi natural log of h plus w over h times, and what I left off here was the current, and I'm going to write that up now as A plus BT, the derivative of A plus BT, and then we have a negative. Okay, so what I did here was when you're taking the derivative, you can pull out the constants, and these terms are all constants. Mu naught, literally a constant, L 2 pi, and then the natural log of h plus w over h will be a constant when all that's changing is the current. So then the only thing we're going to take the derivative of is A plus BT. The derivative of A plus BT, the A goes away, and BT just becomes B. And so we're going to be left with EMF, which is negative d flux dt, equals negative mu naught L over 2 pi natural log of h plus w over h times B, because B is the change in current with respect to time, di dt. Right. And that di dt is the only part that's going to be changing with respect to time for our flux, because we found the flux up here, we plugged it in, took the derivative with respect to time, everything was a constant except the current, and so the current was the only thing we took the derivative of. All right, so now we plug in values, which we'll see how this goes. Negative 4 pi times 10 to the negative 7th, 4 pi times 10 to the negative 7th is what mu naught is. L is 1.2, 2 pi, that's just 2 pi, I suppose. Natural log of h plus w. So h is 1, w is 15. So this is going to be 0.16 meters divided by h, which is 1 centimeter, which is the same as 0.01, times B, which they tell us is 12 amps per second. Yep, got most of the terms we need here. Do some canceling. 2 pi and negative 4 pi become 2. I'm going to write this as, I'm just going to put that into a calculator now. Calculator. We'll go to Wolfram, because it's useful and I like it. So we have negative 2 times 10 to the negative 7th times 1.2 times 12 times natural log of 0.16 divided by 0.01. I know I could probably do that in my head. And we get an answer of negative 9.98 times 10 to the negative 6, and that's going to be volts. Okay, and so, and with the magnitude here, so let's see. Let me check my calculator. That doesn't feel right. Ah, that part. Forgot I put in 1.5 instead of 7.99 times 10 to the negative 6. There we go. Hop. Right there. Negative 7.99 times to the negative 6. Positive because they want magnitude. And what is the direction of the induced current? Okay, so this is negative. So what that's saying is it's going to create a magnetic field. So the EMF voltage is going to drive a current. That current is going to create an induced magnetic field that is going to oppose the existing magnetic field, the original. That negative means oppose as opposed to reinforce. So the magnetic field here is going into the board at that point. And so we're going to create a magnetic field that goes out of the board. And to create a magnetic, you wrap your fingers in the direction of current, your thumb points in the direction of the magnetic field created. And so for this to happen, the current has to go this direction. And that's going to create a magnetic field induced, that is out of the board as opposed to the existing original field, which is into the board. And so that direction is going to be considered counterclockwise. Okay. If suppose we have a constant current of 6 amps, which flows in the straight wire, and the loop moves from an initial position of this towards the bottom at a constant speed of that. Now we want to find the new induced EMF in the loop 1 second after it begins to move. Okay. So I'm going to start from the beginning. So EMF equals negative d flux dt. We know what the flux is, so I'm going to write that up. That's going to be mu naught IL over 2 pi natural log of h plus w minus natural log of h. And so the current is, so all of these are going to be constant. This part right here is going to be constant. So we're going to have mu naught IL over 2 pi over the derivative of natural log of h plus w minus natural log of h. Now, the thing is, h is constant, but w is constant, but h is changing. So we have h initial, which is constant. No, it's not. So both h and, so h is going to be changing here. So h is going to equal h initial plus 26 plus Vt, and h plus w is going to be h initial plus w plus Vt. The idea here is this velocity times time is just velocity equals distance divided by time. Therefore, the distance is going to be velocity times time. So that's going to be the distance that we have for how far away these 2 points are. So this point here, our initial is going to be h naught plus Vt, and our final is going to be h naught plus w plus Vt. So now we can just plug that in. Can we plug that in? I think so. Maybe. All right. So yes. Actually, I might be able to do this a little bit differently. Oh, so everything I said there, totally true. I'm just going to try and take the derivative of this. So mu naught I L over 2 pi. So the derivative, so I'm just going to distribute the negative, is going to be the derivative of natural log of h is 1 over h times the derivative of the interior, so that's going to be the chain rule, dh dt, minus 1 over h plus w times derivative of the interior, also dh dt. We can pull out the dh dt, and we get mu naught I L over 2 pi times dh dt of 1 over h minus 1 over h plus w. Maybe. So the key idea here then is this dh dt is the velocity. H is going to be, as we said before, h naught plus vt, which is going to be, we know that t equals 1 second and 26 centimeters per second. And then the final h is going to be same idea. So I can actually put numbers in this. We're just going to put numbers in this right now. So 4 pi times 10 to the negative 7th times the current, which did they tell us, is it the same current? 6 amps. 6 amps times the length, which I think is constant. It's 1.2, all over 2 pi, times the speed, which I'm going to write as 0.26. That's dh dt, because it's moving at 26 centimeters per second, times 1 over h, which is going to be 1 over 0.01, because it starts at 1 centimeter. Yep, it starts at 1 centimeter. And then it goes for 1 second at 26 centimeters per second. So I'm going to do plus 0.26 minus 1 over 0.01 plus 0.26, because that's the h plus vt. And then we're going to add in w, which we're told is 0.15. 0.15. And this actually should be the answer. So the key idea here was write up flux, take the derivative, look at what's changing. All right. So 2 pi and 4 pi becomes 2. Yes. Now we're going to go straight to calculator. So we're going to have 2 times 10 to the negative 7th times 6 times 1.2 times 0.26 times quantity, 1 over quantity, 0.01 plus 0.26. I know I could probably do that in my head and simplify it. I'm not going to. Minus 1 over quantity. Move that out of the way so I can actually look see what I'm doing. 0.01 plus 0.26 plus 0.15, and that should give us a positive number, a small yet positive number, 4.95. 4.95 times 10 to the negative 7th times 10 to the negative 7th, and that's going to be volts. Yep, they want it in volts. So 4.95 times 10 to the negative 7th. 4.95 times 10 to the negative 7th volts. What is the magnitude of induced EMF 1 second after it begins to move? Check. What is the direction of the induced current 1 second after move? Okay, so this gave us a positive number. Positive, so right there, plus. Positive number, meaning that it's going to reinforce the original magnetic field. So the original magnetic field, get rid of some of this, was into the board. So the EMF, the voltage, is going to drive a current that is going to produce another induced magnetic field that's in the same direction as the original. So to get going into the board, place your thumb in the direction of magnetic field, wrap your fingers, and I know it's backwards because the camera, that's okay, you'll get over it, is this way. So this is going to create a current going that way. It's going to create a magnetic field into the board because it's reinforcing it because we have a positive value here. Basically, that negative distributed, and then when we flip the math clockwise, answer for that is clockwise. So kind of to recap what we did here, we had a loop of wire. We had a loop of wire and a current running through a long straight wire. We used the formula mu naught I over 2 pi r to find the magnetic field of the wire, the long straight wire, current carrying wire, the magnetic field it produced within the loop. And since the loop has a different radius, and magnetic field in this case is dependent on radius, we had to use an integral to find out what the actual flux would be. We then used the formula EMF, voltage, electromotive force, equals negative d flux dt. We had our formula for flux. We plugged it in. We had to be clever, or at least not dumb, with our derivatives. We did that, worked out great. We then had a situation where the loop is moving, and we did the exact same setup. EMF equals negative d flux dt. This time, the distance from the wire was not constant, so we had to look at that d flux, the derivative with respect to t. We took the derivative of our natural logs, and we eventually got an answer, plugged in values, and worked out great. So, bit complicated. Hope that helped. See you next time.